Hey everyone, Houston Math Prep here. We're going to explore level curves and contour maps for functions of more than one variable in this video. We'll start by assuming that you are located somewhere on the surface of the Earth, so you're not on another planet, you're not hovering above the Earth at a particular altitude. If this is all true, then the outdoor temperature, where you're located in this moment, is a function of your location. And your location on Earth, if we want to think of it vertically and horizontally, is really then based on the exact latitude and longitude. So we can think of this measure of how east or west you are and how north or south you are as x and y coordinates. So temperature then, in this instance, what we usually think of as a z value, is a function of x and y. We could report the weather this way. We could put a picture of your specific country in the xy plane inside of 3D space and plot a surface above it, and the z value of your specific location in the plane would then tell you what temperature it is outside, and mass confusion might set in, right? Everyone trying to look at a 2D projection of 3D space and estimate the z value at the place they think is directly over their location in the xy plane. It's probably a good thing that we don't do it this way. What you'll usually see instead is just a 2D map of your region of the globe with various regions of colors everywhere. And based on a key or some type of context, you'll be able to tell that the green region, for example, of the map is everywhere in the 50s. In other words, between 50 and 60 degrees Fahrenheit in my picture here. The next color will represent the next zone of values. So here my yellow is showing everywhere that's in the 60s. And it's somewhat intuitive, right? You might not even realize that your mind says, hey, I'm in the green zone, but I'm kind of closer to the yellow zone, so it must be in the high 50s outside where I am. If I asked you to tell me all of the places on this map that are exactly 60 degrees, could you do it? And I think you probably could. This line or curve in our temperature map that is the boundary between the green zone and the yellow zone, in other words, the exact place where we move from being in the 50s to being in the 60s, tells us everywhere in the country that is exactly 60 degrees. And this is the idea of what we call a level curve. A level curve tells us all the places in the plane, in the domain of our function, in other words, that have the same z value. If you look at this light blue zone above the 50s, this is everywhere on the map where it's currently in the 40s. And the boundary where we go from the light blue zone to the green zone is really a level curve also that tells us exactly where all the z values, in this case all the temperatures, are exactly 50. If we graph multiple level curves together, and the values for those level curves are at regular intervals, so here in our picture all of these level curves are exactly 10 degrees apart from one another, then we call this sketch of several level curves together a contour map. We'll walk you through a few examples of sketching level curves and contour maps for functions here. So we want to sketch a contour map for the function. We have f of xy is equal to the square root of 16 minus x squared minus y squared. We're going to use these values for our contour map. Notice they're evenly spaced 0, 1, 2, 3, and 4. And to find a level curve for a function, all we do is simply take the formula for that function of x and y and set it equal to that value. Okay, so for our k equals 0 here, the level curve where k equals 0, where the function equals 0, we just take our function, square root 16 minus x squared minus y squared, and we're going to set that equal to 0. We can sort of think about then what this is going to look like since we're sketching a map. So maybe if we square both sides, we'll get that 16 minus x squared minus y squared is equal to 0. I could move my quadratic terms over, add them to the other side. I would get 16 is equal to x squared plus y squared. And looking at this, you might notice that this is a circle with radius equal to 4. This is centered at 0, 0. Let's take a look at the level curve where k is equal to 1. So k equal to 1 means taking our same function, square root of 16 minus x squared minus y squared, and setting that equal to 1. When we square both sides here, we'll get rid of our root, and we'll also have that 1 squared on the other side is still 1. If I add my quadratics over to the other side, I'm going to subtract my 1 over to the left side. That would give me actually a 15 over here is equal to our x squared plus y squared. Very similar before we have a circle. that's centered at 0, 0. The radius is not quite 4, it's a little bit smaller than 4. This is going to be 3 point something, right, with the square root of 15 here being our radius. Let's move on to the next one. K is equal to 2. That will give us the square root of 16 minus x squared minus y squared equal to 2. So we want to find all the places where the z value is 2 is what we're doing here. Squaring both sides will give us this thing under the root is equal to 2 squared, which would be 4 here. If I subtract my 4 and I add over to the other side there, then we'll get 12 is equal to x squared plus y squared. So you might see kind of a pattern here, right? We started with a circle of radius 4 here, centered at 0, 0, and you can tell as our level curves get higher and higher values, we seem to be just getting a little bit smaller radius with each one. Let's go ahead and work out the last two. So we'll have with k equal to 3 then. That will give us the square root of 16 minus x squared minus y squared is equal to 3. And if we square both sides, of course, we'll get 16 minus x squared minus y squared is equal to 3 squared, which would be 9. If I subtract the 9, that'll give me a 7 over here. So this one actually ends up giving us 7 is equal to x squared plus y squared. So we still have a circle. You can see our radius, if we square root this, this is going to be 2 point something now. We're getting even smaller still. And then with k equals 4, which is the last one we're asked to find, our level curve is going to be the function just equal to that value. So we have our square root again now equal to 4. And if we square both sides here, we'll get 16 minus x squared minus y squared is equal to squaring 4 gives us 16. And if I subtract the 16 over and move this over to the other side, we really get 0 is equal to x squared plus y squared. We can kind of think of this as a circle centered at the origin with radius 0. This is actually a point, really. This is just the origin itself. So we have circles getting smaller and smaller until we hit k equals 4, and then we just get a point. So let's take a look at what's really going on with our surface and what the level curves are really showing us here. So our function, our f of xy equal to the square root of 16 minus x squared minus y squared, this is actually the graph of that function. It's an upper hemisphere. It has radius 4, centered at the origin. When we're finding the level curve where k equals 0, that's like taking a horizontal plane and cutting through the surface at z equals 0 and seeing what shape of cross-section do we get. You can see we get a circle of radius 4 here. We're cutting just through the very bottom edge of that upper hemisphere. As we then move on to k equals 1, in other words, cut through this surface at z equals 1 horizontally, you'll see we're cutting a little bit higher, so we're going to get a slightly smaller circular cross-section as we cut through it. Going up to k equals 2, cutting through at z equals 2, we get a smaller circle still. K equals 3, we get even smaller still. And it turns out k equals 4 is actually the top value where we can cut through this and just barely get the top point of this hemisphere. Above that, we would actually not intersect the surface at all. So here you can see each of these circles represents one of these level curves, and together, because all of these are evenly spaced, this gives us a contour map with all of these level curves. Let's look at another example here. We're going to sketch a contour map, this time for the function 2x squared plus y squared, and our k values are now 4 units apart for these level curves. So if we go ahead and look at k equals 0, the level curve for that will be our function 2x squared plus y squared is equal to 0. Now we have a square plus a square equaling 0, and the only way that's true really is when x and y are both 0. So this is really going to give us the origin again in this case. So we got it for our first level curve this time. Let's move on to k equals 4. So k equal to 4 will give us our function 2x squared plus y squared equal to 4. And this looks similar to a circle. It's not a circle though, because these coefficients for the square terms are not the same. This is actually an ellipse. The way we normally see an ellipse would be to get equal to 1. So if I divide everything through by 4 here, I'm going to actually get x squared over 2 plus y squared over 4 is equal to 1. And if we know things about ellipses, we can then graph this ellipse. Of course, this is going to be stretched a little bit longer in the y direction than in the x direction here. This is going to be an ellipse. Let's go ahead and look at k equals 8. So k equal to 8 here. That will give us our function 2x squared plus y squared is equal to 8. We'll do a similar thing here. We'll divide by 8 to make this look more like a usual ellipse equation. So we get x squared over 4 if we divide by 8, plus y squared over 8 is equal to 1. You can still see it's a little bit longer in the y direction than in the x direction. So it's going to be an ellipse. Again, this one's a little bit larger. So remember, our cross sections were getting smaller circles last time as we went along here. As our k is getting bigger, we're actually getting larger ellipses. Go ahead and look at our last one here. So we also have k equal to 12. Setting our function equal to 12, 2x squared plus y squared is equal to 12. Dividing again, you can see we get a similar thing, right? We'll divide by 12 this time, so we actually get x squared over 6 plus y squared over 12. If you graphed these, you'd have to figure out what the square roots of these are and give some approximation when you're drawing it. But this is going to be an ellipse again and a little bit bigger than the ones before it. So if we actually show now the graph of our surface, this function, so our f of xy equals 2x squared plus y squared, this is actually an elliptic paraboloid, and it opens upward from the origin in 3D space. Since it opens upward from the origin, you can think about k equals 0. If we cut through the paraboloid at z equals 0, that's just going to cut through the very bottom point of the paraboloid at the origin. So our level curve for k equals 0 is just going to look like the origin, like that point that we said earlier. Cutting through at k equals 4, a little bit higher up, you can see we get a nice ellipse cross section as we cut through it. As we mentioned before, it's a little bit longer in the y direction. That's the major axis. The x direction is the minor axis here. If we cut higher up, k equals 8 would be cutting through at z equals 8. That gives us a little bit larger cross section, still an ellipse. And k equals 12, cutting through with the plane z equals 12 gives us a bigger ellipse still. So here you can see these are 4 level curves for this function. At these values, since they're evenly spaced, this is what we call a contour map. Looking at our next example here, we're going to sketch the level curves for the values 0, 2, 8, and 18 for this function. This is super similar to our last function, except we have turned the add into a subtract. You see it does a little bit of a different thing for us there, but let's go ahead and solve our first level curve, k equals 0. So slicing through this function at z equals 0 will give us a cross section of the shape 2x squared minus y squared is equal to 0. Now this is a case where we have one positive term and one negative term that are squared, so this is not a case where it's just the origin. Here I'll go ahead and add my y squared to the other side. We'll get 2x squared is equal to y squared. If I want to solve for y, square rooting both sides then, right, would actually give me plus or minus the square root of 2x is equal to y. And so these are actually going to be lines, there's 2 of them, with slope positive root 2 and negative root 2. And they intersect at the origin. So these are going to be intersecting lines here. If we look for this next one here, k equals 2, so slicing through our function at z equals 2 gives us cross section 2x squared minus y squared is equal to 2. And now here, this is no longer going to be a case of 2 lines. If we go ahead and divide this by 2, you might see what this is. X squared minus y squared over 2 is equal to 1. This is actually a hyperbola. And if you remember things about hyperbolas, because the x squared term is positive, these branches open the x direction. This is technically over 1. If you remember, this a square here is basically telling us that's how far it is from the center to the vertices on your hyperbola. So some things you might want to remember about conic sections as we start to graph some of these level curves. Let's do k equals 8. That's going to give us a similar thing to what we had before, but the number on the other side is going to be different. So instead of dividing by 2 to get this equal to 1, which we usually do for hyperbolas, we'll go ahead and divide by 8. That'll give us x squared over 4 minus y squared over 8 is equal to 1. And here you can see, again, this is a hyperbola. You can see that our vertices, this is 2 squared, so our vertices are 2 units away from the origin there, opening in the x direction. Looking at our last value here at k equals 18, so cutting through this surface here at z equal 18, we get 2x squared minus y squared is equal to 18, and then dividing by 18 is going to give us a similar thing. We have x squared divided by 9 then, minus y squared divided by 18 is equal to 1. So again, we get a hyperbola. You can see that the a square underneath x squared is 9, so that means that's 3 squared. We would have vertices that are 3 units away from the origin, still opening in the x direction. If we now graph our function, our z equals 2x squared minus y squared, this is actually a hyperbolic paraboloid. It's a saddle shape. You can see this if we're zoomed in. We zoom way back out now because we have some large z values we need to account for here. So this gets pretty monstrous vertically, but as we cut through at z equals 0, you'll notice we get that intersection of 2 intersecting lines there. As we slice through a little bit higher at z equals 2, that plane, you'll see we do start to get that hyperbola shape. As we slice through even higher at z equals 8, you can see our vertices start moving away from the origin there, from the center, and then at z equals 18, our k equals 18 level curve, we get vertices that are even farther out and a slightly different shape of parabola there. Let's look at our final example. We're going to do a contour map. Notice that our k values for our level curves are all 6 apart here. Our function is fxy equal to 6 minus 3x minus 2y. So we'll just start setting these equal to these values. So z equals -6. That's our first plane that we're going to slice through. So we'll set our function 6 minus 3x minus 2y is equal to this -6. And to sort of make sense of this, maybe if I add the 6 over to be with the other 6, we'd get a 12 there. And if I move my variable terms over to the other side, we get something like 12 is equal to 3x plus 2y. I think we can see this is a line. You could put this in slope-intercept form if you want to graph it, or you could use the intercepts to graph if you want, but this is a line. Looking at k equal to 0, if we set our function of x and y equal to 0, 6 minus 3x minus 2y equals 0, there's really nothing to combine as far as constants go, so if I just simply take our variable terms over to the other side, we get 6 is equal to 3x plus 2y, and what you'll start to notice, I think, is actually when you solve these, you're going to get the same slope, but you're actually just getting different intercepts for these. So this is also going to be a line. It will have the same slope as the other one. So for k equals 6, I think you can see something similar probably happens as well. 6 minus 3x minus 2y equal to +6. Now if I subtract the 6 over there, I'll get 0 for this is equal to 3x plus 2y. Of course, this is going to go through the origin, I think, if you try and figure that one out there. That's a line also. Let's look at our last one, our level curve where z is equal to 12. So k equal 12 here, we get 6 minus 3x minus 2y equal to 12. If I subtract the 12 over, now I'm getting negative numbers here, right? I'm getting -6 is equal to 3x plus 2y. You can see we're going to start getting some negative intercepts there, so we move out of quadrant 1, I think, with our line. So as we start looking at our function here, the graph z equal to 6 minus 3x minus 2y, you may not have already noticed this is the equation for a plane. So we get a plane here. It cuts through the first octant just a little bit. And remember, we were getting lines with the same slope for our level curves for this contour map. So when k was equal to -6, we were slicing through the plane at z equals -6, so we're actually slicing below the xy plane, and we get this nice line here with slope, it looks like -3/2. For k equals 0, our level curve is actually the cross-section we get exactly in the xy plane itself, because z equal to 0 is the xy plane, so we get another level curve there that is a line that is parallel, has the same slope. Here is slicing through at z equal +6. We go through the origin actually with this level curve, and then z equal to 12, we get a similar thing as well. If we start talking about a function of more than 2 variables, then our idea of level curves has to be expanded to what we call level surfaces. So here we've got a function of 3 variables, x, y, and z, and this tells us that our domain would consist of points in 3D space. We would need to plug in an x, a y, and a z value to get a value from our function. So if we try to imagine the graph of this function, it would be a 3D object inside of 4-dimensional space. Not easy to picture here, right? But we can gain some understanding of what's going on by looking at the level surfaces of this function. So if we were to set our function equal to different constant values k, then these level surfaces would actually be spheres centered at the origin. So if you take it back to, say, our temperature analogy from the beginning of the video, let's say this was a temperature function. If you're at the origin, right, 0, 0, 0, plugging in 0 for everything, then it's 0 degrees at the origin. But if we start to increase the k value, then we would be on spheres with a bigger and bigger radius. In other words, farther and farther away from the origin in 3D space. And that tells us it would be getting warmer and warmer as we move away from the origin in R3. All right, everyone, good luck with your level curves, level surfaces, and contour maps. Thanks for watching. We'll see you in the next video.